And we have 5 lectures planned, of which this is the first of 5 this summer. And my co-host is Ruth Indrick from Kennebec Estuary Land Trust, and she's in the table in the back, and she's helping me with the Zoom and the chat. So she's going to be the Zoom host and taking care of all of our Zoom participants. And without further ado, I would also just like to say, please silence your phones if you haven't already, because your Zoom participants will hear everything in the room, not just Dave or me with the mic, but everybody. So they'll hear the background noise, etc. So please silence your phones and enjoy. When Dave is done, we will have Q&A, and we will try to go back and forth between Zoom participant questions and our audience in-person questions. So welcome, and let me introduce Dave West. He's a professor of geology at Middlebury College in Vermont, who specializes in unraveling the bedrock geologic history of the northern Appalachians, with a particular interest in coastal Maine geology. A North Carolina native, Dave obtained his master's and PhD in geological sciences from the University of Maine, and has been conducting geological research in Maine for over 30 years. Prior to arriving at Middlebury, Dave taught at Bowdoin College, Lafayette College in Pennsylvania, and Earlham College in Indiana. So, warm welcome for Dave.
Your computer picks up your voice with a sound.
I will. Thank you, Dorsey, and thank you for having me. I guess I'm the guinea pig here, so can everybody hear me? Okay. I don't know if the Zoom folks can hear me or not, but we're going to roll anyway. But yes, thanks for the introduction. And basically, I'm a historian. When I first went to undergraduate in North Carolina, I thought I was going to be a history major. And the first class I was in had about 250 students in it. It didn't work out really well, but I took a geology class that was smaller. We took field trips, and I soon came to realize that geologists are historians as well. They just study the history of the earth rather than history of civilization or people or things like that. And so it really sort of melded two things together, my love of the outdoors and my love of history. So that's how I got started with geology. And so what I'm going to talk about today is really trying to give you a little bit of an overview of what we know about the geologic history of the Casco Bay area. And there are a number of sort of, I guess, sophisticated techniques that geologists use. Some of them are brute force techniques, some of them are more sophisticated techniques. So I'll try to talk a little bit about how geologists go about unraveling the multi-million year history of the earth. I mean, the rocks that we're sitting on here are hundreds of millions of years old. So how do we know how these things form? How do we know what sorts of geological processes were operating in this area in the past? So I'm going to try to give you a little bit of information on how geologists work. And then my second goal is to then use some of those tools to give you a little bit of an overview of the geologic history of this particular region, which is very, very rich. So the rocks are our history books. All these rocks that form, the ones that we're standing on here, the ones that are all around, they record information about the processes that were occurring when they formed. Did they erupt from a volcano? Was it sediment on the ocean floor? Were they miles underground at some time? Was it hot magma? All of that stuff is recorded in the rock record. So you just have to know how to read them. And that's what geologists do, is read the geological record, whether it be from rocks or sediments. It depends on what kind of information you're trying to get. So I study the bedrock, the ancient history, the 100 million year old history of this area. Other colleagues study the glacial history, which is thousands of years old, tens of thousands of years old, that may tie that into climate change. But my main area of research has to do with the 100 million year old history of this particular area. So all rocks have a story to tell. There are many different stories that are being told by the rocks around here. The types of rocks, there were volcanic eruptions here. The area was much like the San Andreas Fault Zone in the past. This used to be underwater, an ocean basin. So all of that information is out there in the rocks. This is a slide to remind me to thank some of the people who have helped me along the way. And first and foremost, the Maine Geological Survey has supported my work of detailed geologic mapping and research for over 20 years. And so I really appreciate their help. This is a map of the Bath quadrangle, the Bath area. And my co-author there is Arthur Hussey, who passed away about 5 years ago, but he did a tremendous amount of work along the coast of Maine, really from Kittery all the way up past Booth Bay Harbor. He was a geology professor at Bowdoin College for over 35 years. He laid a lot of the groundwork. So a lot of the work that I do, I'm going sort of in his footsteps and filling in holes, providing more detail, using some more sophisticated analytical techniques that have come up in recent years. But that was sort of the foundations that were laid in this particular area. So I want to talk a little bit about sort of how we go about studying these rocks. This may be an area that some of you have driven by, a new construction site. I guess I haven't been back there in a year or so. Maybe it's, I don't know, is it high school opened yet? But they have tremendous outcrops there. They blasted away the side of the hill there. And for me, I remember coming around the corner and I was like, oh my goodness, look at all that rock there. And I went back there and I collected a number of samples, but it's a treasure trove of information, as is the coast of Maine. And for those of you on Zoom who can't see me, that's what I look like. There's a rock that I collected from back behind the Bath excavation site there. This is a closer look at it. There are really some pretty cool rocks. They're banded. All these little pink layers that you see in the rock here are garnet rich. They're just tiny little garnets that are concentrated in those little pink bands in there. And the black is black mica or biotite mica. Looking at it even closer, this is a microscopic view of those rocks. You can see the scale bar down in the lower left. That's 1/10 of a millimeter there. So there you can see one of those garnet crystals, those sort of pinkish crystals there. And you can see they're compositionally zoned. You can see the center part's got a lot of little inclusions in it, and the outer part is clean. So we can, look at these rocks in excruciating detail and decipher information. So we're getting more and more depth of information as we look at that. Here's another view of the same rock that I collected back behind the Bath High School. Beautiful amphibole crystals, biotite mica there. So there are a lot of different ways that we can go about looking at these particular rocks. So the rocks of the Casco Bay region are history books. There's a lot of information preserved in there, and I'll try to go over a little bit of that today. This is a bedrock geologic map of Maine. You can see the star there that's unlabeled is about where we are here. All the different colors here represent different rock types. A lot of those blue colors you see along the coast you'll recognize as granite bodies. A lot of the other colors are metamorphic rocks. These are rocks that were once igneous rocks. Maybe they erupted out of a volcano, or sedimentary rocks. Maybe they were deposited on the ocean floor that have since been buried and cooked and pressurized and transformed into different rocks. So that's where those garnet crystals come from. They grew in a metamorphic rock. This is, believe it or not, this is what the Earth's surface, as best we can tell, looked like about 470 million years ago. There was an ocean basin that existed prior to the Atlantic Ocean. It's kind of a leap of faith. You're going to have to take me on this, but I'll talk a little bit more detail about this. But the rocks that eventually came to be in the Casco Bay area actually are what we sometimes call exotic terrain rocks. They're rocks that weren't formed on the North American continent. They were formed out in some ocean basin. So you can see that the big continental landmass you'll recognize, Africa and South America welded together. It's called a supercontinent called Gondwana there. Laurentia, which is at the top there, is the ancient North American continent. So this area is preserving rocks that were formed out in the middle of this ocean. So if you think about the Philippines or Japan, something out in the Western Pacific Ocean, if that eventually got slammed into Asia, That's kind of what we're talking about in terms of the rocks in this area. They formed out in the middle of this pre-Atlantic Ocean hundreds of millions of years ago, and then were welded onto the side of North America through plate tectonic processes. So the analogy that we have, and I'll talk a little bit about why we know this, is that probably the rocks in this area originated in kind of an active Western Atlantic or Western Pacific Ocean basin where there was a lot of volcanic activity, a lot of earthquake activities, tsunamis, very active area out there. And then eventually they got welded onto North America. So there were violent volcanic eruptions, probably proximal to the ocean. There were sediments being deposited on the ocean floor, mixed in with volcanic debris. So here's an example of a explosive volcanic eruption going out in the ocean. This is probably the way a lot of the rocks around here began their lives, essentially. And we can see textures and features preserved in the volcanic rocks around this area that are exactly like what we see in active volcanic areas. So I'll talk a little bit more about how we make this leap or how we understand origins of particular rocks. So I have to talk just briefly about plate tectonics, which is really what sort of facilitated all of this activity here. So the solid Earth is moving beneath us. The Earth has plates. I always hesitate using this analogy, but one of my professors a long time ago talked about, imagine if you had a bowling ball and you covered a bowling ball full of, completely with Vaseline and then put pizza slices on top of it. That's plate tectonics. So the center is kind of a solid, and you've got this Vaseline layer, and you've got these pizza slices that are moving around and crunching into one another. That's kind of plate tectonics, and it's been going on for, as far as we know, billions of years on this planet. So plates move, they come apart, they come together, and ocean basins open and close over time. Ocean basins are pretty, short-lived features. The Earth is 4.5 billion years old, but the oldest ocean basin is only about 180 million years old. So oceans come and go. The continents stay, but the oceans come and go. So that's part of the process. So the rocks record all these different plate tectonic processes. So plate tectonics results in these movements of plates. The plates rift apart, they slam together, they grind sideways next to one another, and a lot of these large-scale geologic phenomena are the result of plate tectonic processes. This is a map that shows the distribution of the Earth's plates now. So these are the pizza slices, all different sizes and shapes. They're all moving around on top of that Vaseline on the bowling ball, interacting with one another. They're constantly moving. If we went back 50 million years ago, they wouldn't all be the same sizes. They wouldn't be all in the same positions because they're constantly moving around. And certainly if we go back 470 million years ago, which is the age of a lot of the rocks around here, it's a very different situation. Where these plates are interacting with one another, where they're coming together or pulling apart is where a lot of the action is. That's where the volcanic eruptions are, most of them. That's where a lot of the big earthquakes are. So if you look at the South American continent there, and then the cross-section on the left, the bottom left there, you can see that oceanic material is diving underneath South America. It's getting destroyed. So that's the oceanic material that doesn't last very long. The continents, they're kind of like beach balls in a swimming pool. You can't push them under. You can't get rid of them. The oceanic material is kind of like it's like a piece of I-beam or something. It's just going to dive under the water, so it's heavy and dense. So a lot of our activity that we see now is the result of this plate tectonic activity. Most of it is where plates are coming together. We go back to this diagram of the different plates. If you look at the North American plate, notice how the eastern margin of North America isn't at the edge of the plate. The North American plate actually is partly continental and partly oceanic. So that's why, well, I think sort of where we are now is geologically boring in terms of active, there's not any big earthquakes or volcanoes or tsunami or anything like that. It's a fairly safe place to live in terms of big scale geological processes. And that's because we're not on a plate margin. Whereas if you go to the western side of North America, notice there are some heavy dark lines over there. We are at a plate margin there. So you have Mount St. Helens, Mount Rainier, you have the San Andreas Fault System, a much more dynamic plate setting. So it really depends on where you are in time and space in terms of plate tectonic activity. So again, the rocks in the greater Casco Bay area began their lives out in the middle of an ocean basin, similar to, say, the Philippines or the Marianas Island arc out there 480 million years ago, and then eventually got welded onto North America. So if we go back here, the GA there stands for Gander Terrain. It's a term that people use regionally throughout the Appalachians for these particular rocks. So this is 470 million years ago. Watch that GA, it goes in and slams into North America. It takes it 30 million years to get there, but it's geological processes. But when it did hit, it hit hard, and it caused a lot of deformation, metamorphism, and so that's kind of the story there. And then eventually, Gondwana, which is down in the southern part of that map area there, eventually that comes in and slams into North America, and the whole thing is welded together. So that Raic Ocean Basin or Iapetus Ocean Basin eventually closes, and eventually it'll have to open up again to form the Atlantic. So ocean basins come and go. That's kind of one major thing there. And then after these things slammed in there, a lot of the, we're talking about head-on collisions and pulling straight apart, but there's a lot of sideways movement to this as well. So there's a major fault system that runs really from New Hampshire all the way up into New Brunswick. It's called the Norumbega Fault System, and it's a whole network of faults. Now, you don't have to be worried about it. Well, I guess it could have an earthquake, but it's not as active as the San Andreas Fault Zone by any means. It was mostly active 300 million years ago, but it was a major strike-slip fault system, just like the San Andreas Fault System. So how do we figure all this out? I want to sort of step back a little bit and talk a little bit about that. Geologists sort of use a premise, and that is the present is the key to the past. So we look for things that are going on now, and then can we see those same things in the rock record? So for example, in this diagram here, we've all seen ripple marks. You walk on the beach, you see ripple marks. You can look at ancient rocks and see those exact same ripple marks. So it's not a real stretch to say those rocks on the right there, which are hardened sandstone, which are millions of years ago, millions of years old, probably formed in environments similar to moving water back and forth. So the present tells us about stuff that's preserved in the rock record. Middlebury College here on the right here, we've got a bunch of limestones on campus there. Limestones really only form in shallow marine environments. Vermont, unfortunately, is not a shallow marine environment like the Bahamas right now, but it was hundreds of millions of years ago. That's why those limestones are there. So limestones only form in those environments. We look at the present and it tells us something about the past. Same thing with volcanic rocks. On the right there is a beautiful volcanic rock from near Kennebec Pond, just north of Union, Maine. Looks exactly like a rock that erupts out of a volcano, texturally. So we look at that rock and say, must have come out of a volcano, huh? So it's pretty straightforward in terms of using the present as a key to the past. On the right there is a microscopic view of tiny crystals that formed in a volcanic rock in Casco Bay. Looks exactly like a microscopic view of volcanic rocks that form in active volcanoes. So every rock tells a story. This is again that geologic map that I showed earlier. You can see the different colors here represent different types of rocks. And I'm just going to kind of go through and show you a few examples of things. So the little red box is going to be a sort of a key to where some of these things are. So here's an outcrop of rocks along the New Meadows River. Very rusty, weathering metamorphic rocks. It's called the Bethel Point. Remember the Bethel Point formation here. We'll look at a different rock type, this tan-colored rock. This is called the Cape Elizabeth Formation. Here you can see a real swirly pattern, kind of a mixture of granites and metamorphic rocks there, very hot. Look at all the little folds in there. This rock got crumpled during plate tectonic activity. And then all these pink blobs in here represent granites. So these are igneous rocks. So these were molten magmas that formed. This one's probably about 400 million years old. So there's so many granites around here. I want to say a little bit about those. Granites are igneous rocks. They do form from magmas, and most people think of, when you think of an igneous rock, you think of something coming out of a volcano, lava that's flowing out of the Earth's surface. Most magma actually never comes out of a volcano. It freezes before it gets to the surface, freezes underground because it's cooler when it gets up to the surface. That's what a granite is. It's magma that was trying to come up towards the surface, but it froze before it got to the surface, and it froze deep underground. So why do we see it now? Well, we eroded off the top there. So that's one of the advantages of studying the rocks around here. You might say, why do you want to study something that's 400 million years old? Well, there have been miles of material that have been eroded off the top of this over hundreds of millions of years. So we're seeing the deeper parts of things like the Himalayas, like the San Andreas Fault Zone. So these granites, once formed deep underground, then all the erosion that's occurred over time, wind, water, ice, stripped off that top surface. And so now we're seeing those granites at the surface. So when you walk through the area and you see these granites, it was magma, it was molten rock. It just didn't come out of the volcano. So that's where all these granites come from. So once the geologic maps are made, that's the first step. What kind of rocks are we dealing with here? Are they igneous rocks, metamorphic rocks that come from a volcano, they get deposited on the bottom of an ocean? Once you map the spatial distribution of the rocks, then we can begin more detailed studies. We can look at them under the microscope. There are geochemical ways to analyze these samples, so we can take rocks back, crush them up, and determine the trace element geochemistry of the particular rocks. That can provide some useful information. For example, the volcanic rocks around here. Volcanic rocks form in a variety of different plate tectonic settings. Could be along South America in the subduction zone there. Could be out in Hawaii, out in the middle of the ocean, not associated with the subduction zone. Could be Iceland, could be East Africa. There are lots of different places where volcanic rocks can form. So how do we know what kind of environment these volcanic rocks formed in? And this just sort of shows all the different places where you can get volcanic activity. So on the left there is the tectonic setting for the Casco Bay volcanic rocks, but you can see there are volcanic rocks that can form in lots of other areas. They don't form in the middle of plates generally unless there's a hot spot, so that's why we don't have any volcanic activity here. I'm not going to go into the details of this, but this is just one of these fancy geochemical diagrams. These are some trace elements that are only present in parts per million in volcanic rock. And what people do is they go to places like Iceland or the Marianas or the Andes, and they analyze volcanic rocks where we know where they came from, and we study the trace element distributions in those rocks, and they form patterns or groupings. So then I can look at an old rock, do the trace element geochemistry, and see where it plots relative to modern rocks. So you can see this diagram here has different sort of subdivisions depending on where these particular rocks form. You can see that the Casco Bay rocks all plot down in this oceanic volcanic arc. So I mentioned the Marianas out in the Western Pacific, the Philippines. They don't look like continental volcanic arcs like in the Andes. They don't look like Hawaiian. but they do fit with the oceanic model. So that's how we can kind of place these things into a more detailed plate tectonic context. How do we know how old these things are when we're talking about 470 million year old rocks? A lot of these rocks contain tiny little crystals called zircons, which incorporate uranium into their structure. That's radon. Some people probably have radon problems around here because there's small amounts of uranium in these rocks. These particular crystals concentrate that uranium in them. Uranium is radioactive. It decays away. We know the half-life. So if we can measure the amount of uranium and the parent or the daughter product, lead, we can use that radioactive decay. It's like carbon-14 dating, except it uses a much greater half-life. Then we can analyze these crystals and figure out how old they are. So there's a lot of this uranium lead dating that gets done. So now we have an age. Now we have a plate tectonic setting. And we have this information from all over the place, all up and down the Appalachians, from Alabama all the way up to Newfoundland. Everybody's working on things. People working in Vermont, people working in Maine. So this is a collective diagram. It's not just based on Casco Bay. Casco Bay is one piece of this puzzle. But there is consistency to it and allows us to sort of put it all together in this fashion. This is kind of a tectonic model that Professor Hussey put together, and it fits quite well with what we're seeing in the area. So again, you can see there's a subduction zone going under here. It generates volcanic material that erupts at the surface. Some of it crystallizes underground. A lot of it goes out into the ocean, deposited as sediment on the ocean, volcanic material on top of that. So this is kind of the model. I'm not sure why I was cutting out there. So this was a sort of a volcanic arc system that existed offshore of North America. Now, rocks, when they originally form in flat layers. So when they get deposited, maybe a volcanic flow comes out, it's going to be fairly flat, or something gets deposited on an ocean basin, it's pretty flat. So the rocks generally, when they've been undisturbed, look like this. These are much improved, obviously. These have been crunched. So somebody like me, I like structural geology. This to me is, well, it's cool, but it's boring to me because they're flat. Nothing happens to them. I like when things get crashed into. So you can see this big fold here. We see the same thing around here. They're folds. We don't have quite the exposure that we do out west. But these rocks, see these layers? They're straight up. They were originally deposited as flat layers, and now they're straight up. So they got crunched when that volcanic arc formed, eventually slammed into North America and squeezed everything in between it and created these vertically oriented rocks. Whenever you're walking around and you see these layered rocks, take note of the orientation of those layers. I bet it's going to be inclined in some way because they're folded around. And, the sort of the character of the land, the shape of the land, it's not a coincidence or not happenstance. The orientation of all these peninsulas is parallel to the orientation of these rock layers. You can see it at all scales. I could show you a microscopic view, and all the minerals will be lined up. And they're all lined up, in that northeast, southwest direction. All those long peninsulas that you go up and down, they're because things got crunched in this direction. So everything's lined up like this. So these rock layers here are oriented in the northeast, southwest direction. All the peninsulas oriented that way. And if you look at a geologic map, you can see the distribution of the different units are oriented that way. All these heavy dark lines here represent faults, ancient faults where rocks were sliding and grinding past one another. So that in addition to being an ancient volcanic environment, this was also a huge fault zone system. So all these heavy dark lines on this map, and you can see how the geology sort of changes color near where those lines are. This is the Norumbega fault system that existed. So after these rocks came in, they then started shearing sideways, just like in California. And so this was an ancient, major fault system in this area that was active after that initial collision. So the whole Casco Bay area represents a collection of faults that were active at that time. And these extend all through there. So after all of this stuff, eventually Africa and the rest of that Gondwanan continent collided with North America. Now it hit more in the southern Appalachians. So this is what things looked like about 225 million years ago. All the continental landmasses were together in one big supercontinent called Pangaea. So that Iapetus ocean basin that used to exist there closed, and everything got crunched in there. Now, we know we now have an Atlantic Ocean between Africa and North America, so we had to pull this thing apart. So that was another tectonic episode. So basically, we had a situation that was a lot like East Africa. East Africa is pulling apart. If we could come back to this area in about 10 million years, there would be an ocean basin between part of the eastern part of Africa there. So you can see here that if we roll forward to about 150 million years ago, see how Africa is pulled away. And now the Atlantic Ocean is starting to form. So that's where the Atlantic started. The Atlantic is a relatively young feature on the Earth's surface. So there was an ocean, the Appalachian Ocean, where the Casco Bay rocks formed. It closed, crunched everything up, formed that supercontinent, and then it had to open back up. So when it opened up, it allowed magma to come up through there. So a lot of times you'll see these dark colored, they're called dikes, that cut through the rocks. This was magma that came up through there. If you've ever been to Giant Steps, that's a big one. That dark rock that cuts through there, that's formed from that rifting apart that created magma during that East African rift episode. There have been some volcanic eruptions in East Africa in the last year that we have read about that are related to that same process. Now, my area of study is this ancient bedrock, but I want to say a little bit about the glacial history there because it's also a very rich history. So there's a major difference in the age of the material. So the bedrock down here on the bottom is hundreds of millions of years old around here. But the loose material on top, the sand, the gravel, that nasty blue clay, that's all relatively young. That's less than 25,000 years old. It's basically left over from the last glaciations. So we have a sort of a twofold geologic history preserved in this area. We have this really old bedrock history, and then we have this glacial history. So 20,000 years ago, I've been talking about millions of years, 20,000 years ago is nothing. But this is what we think basically the Northern Hemisphere looked like 20,000 years ago. So talk about some radical climate change. Obviously, it had to warm up quite a bit over the last 20,000 years to cause this ice to retreat. But this is a situation, and where's Maine? It's under the ice. You can't see it. It was completely buried at that particular time. So here's another view of it about 20,000 years ago. Ice extended all the way out to Georgia's banks out there. So it went out over the ocean. It was ice rafted out over the ocean. You can see the present day coastline there. And this created a lot of different features. So there are other people who map the superficial history. So I map the bedrock. I get mad when I see all this sand and gravel on top of my rocks. I can't see it. They don't like to see my rocks because then we don't have the sand and gravel from the glacial deposits. So we're all have different sort of desires in terms of what we want to see in the field. These different colors represent different kinds of glacial materials that were deposited in a particular area. So glacial till, the glacial erratics around, and you see these boulders come, they float on it, and they get carried by the ice melts, they drop down. So this rock has nothing to do with what's underneath it. It was carried along for a ride. There's sand and gravel deposits that are deposited in many areas. that form from outwash from the glacial material. This glacial activity is only one of many advances in retreat. So I could give a whole other lecture on climate change, but this is a look at how climate has changed over the last 1.8 million years. So you see this line going up and down. Any time where that line is high represents a time where it's relatively warm. Where it goes down low is where it was cold or glacial period. So there have been multiple advances in retreats of glacial ice over time. So we think about the Ice Age as only being one episode of glacial advance. There have been multiple episodes of glacial advance in this area. So right now, we are on the extreme left there. We're in a warm period of time. Over time, you would expect it to cool off and go back down into a cool period. But the question is, how high is that spike going to get? And it'll be probably a few thousand years before it starts to head down. If the past is any key to what we might expect in the future, we're going to see a lot of waxing and waning of glacial activity. So this glacial ice also has a major influence on the landforms in this particular area. When that ice goes over the bedrock, there's loose material down at the bottom. It's just like sandpaper comes over. So you may have seen glacial striations. One of this cut off on me. Anybody here? Can't hear? Not yet. Well, I'll just keep talking loud. So the glacial ice comes over the top and will carve down the bedrock. So this, you may see this exit. It's the Biddeford exit off the turnpike. You can see the beautiful smoothed off surface of the granite. That granite is, people here now, a little bit. Hello. I'll just talk loud. So that granite there is 380 million years old, but that top surface was smoothed off by the glaciers multiple times, the last time about 20,000 years ago. Here's some beautiful glacial striations on the top of this rock surface here. They are oriented in the direction of ice flow. So that ice moves over, little pebbles are caught underneath, and it drags them through there and creates these surfaces. This is what Maine looked like about 12 to 13,000 years ago. So you can see the little lines on there. That represents the time of ice retreat. So you can see that line that comes through Casco Bay is about 14,000 years ago. That's where the leading edge of the ice moved back. So the ice moved back slowly across the state of Maine over time, and you can see those dark lines represent the retreat rate of the glaciers. So it didn't get back to Mount Katahdin until about 12,000 years ago. So now the weight of all that ice, if you get a mile of ice, it's a tremendous amount of weight. It actually pushes that pizza slab down into the Vaseline a little bit. And then when the glacier moves back, it takes a while for the land surface to pop back up. So what happens is that delayed reaction for the crust to rebound back is that much of eastern Maine was covered in seawater 12,000 years ago. So once the ice retreated, sea level was much higher. So this is what the Maine coastline looked like about 13,000 years ago. I'll stop yelling now. Which is pretty cool to think about. So you went from a mile of ice to being under 200 feet of seawater in about 5,000 years. So it's pretty extreme climate change, obviously. And so since we were under all this ocean water, which was choked with sediment from all the glacial ice that was churning up the bedrock, we get all these big, nasty clay deposits all over the place. So this blue clay, Subduction formation, very unstable, prone to landslides. That was the ocean floor there about 12, 13,000 years ago, just sediment just piled up on top of the bedrock. even woolly mammoths were around here. So this is a paper I found about a woolly mammoth deposit or fossils that have been formed. So you can find marine seashell fossils. You can find other types of fossils that are present in logs, woolly mammoth, that are present in this glacial mud that are out there. So what an amazing history this area preserves in terms of the geologic history. Lots of different stages to it. Started off its life as explosive volcanic eruptions in a sort of a Philippines-type volcanic arc out in the ancient ocean that preceded the Atlantic Ocean. Eventually, those rocks got slammed into North America, welded on, and then things started moving sideways in this big San Andreas analog, the Norman fault system, which ground everything sideways. Eventually, other masses came and piled onto the side of North America, buried the rocks, metamorphosed them, deformed them, and then eventually started to pull back apart. You had this rifting, you had volcanic activity, you produced these dikes that you see in a lot of the rocks around the areas, like giant steps, that records the pulling apart in the early stages of the opening of the Atlantic Ocean. And then eventually we were covered with a mile of ice during the last glaciation. That then led to depressed crust. Eventually, sea level moved much inland, so then we got all these clay deposits on top of that. And even more mammoths roaming around. So quite the geologic history in this area. It's been really fun trying to figure it out, and we don't have all the answers yet. I kind of presented a coherent story here, but we're all fighting amongst ourselves about tweaking the model a little bit. We're all constantly getting information. I'm currently mapping over in the Bristol, Pembroke Point area, trying to get more detail on it in that area. I usually have Middlebury thesis students who work with me, the colleagues at Bowdoin College who I work with, also at the University of Maine. So there are a number of us who are working on various parts of this geologic history. So with that, I think I will end it and ask for any question. I'm not sure how we're going to handle the Q&A here, whether we're going to go to the Zoom or the live audience. But yeah.
Thank you.
So what we're going to do is we're going to do a combination of Zoom questions and in-person questions. So we'll start with a couple of in-person questions for Dave. Yes, Foreman?
Is the Atlantic slope expanding?
Yes, it's moving about an inch a year or so. We're getting further away from Europe. But eventually, it's going to close back up. So it'll get fun around here again if we wait long enough. Eventually, things will start to subduct. So ocean crust, when it forms initially, is hot, fairly buoyant, and then when it moves up that Mid-Atlantic ridge, it gets colder, it gets more dense. And so remember how I showed how the North American continent was both continental and oceanic? Eventually, that oceanic material is going to get so heavy and old and dense, it's going to subduct that. So some of the oldest ocean crust in the world is off eastern North America. So it's ready to go, but we probably won't see it. Yeah?
You said the Earth is 4.5 billion. Is that when the Earth started to solidify, the make rock, or is it single? What is the definition of the beginning of the Earth?
Yeah, so the question is with regards to the origin of the Earth and how do we know it's 4.5 billion years old in that time period. So that's based a lot on sort of meteorite data that's sort of related to the sort of primordial material in the solar system. So when we date those things, we get those kind of ages. But yeah, that is the age when it eventually sort of through accretionary processes formed initially. Now, there wasn't any continental crust at that time. Most of the Earth was molten, so it took a long time, hundreds and hundreds of millions of years to sort of cool off enough to form any solid rocks, really.
When did that happen?
Well, there are some zircons that are about a little more than 4 billion years old. So there is some evidence that you started to form some continental crust early on. But over time, the continents have gotten bigger. So initially, they weren't as big, but over time, they've grown. Not my main area. I mean, I study 450 million year old rocks, which are old enough for me. There are a lot of people who go to places like the Canadian Shield and Australian Outback. That's where a lot of these really old rocks are. And they try to understand, when did plate tectonics start? When did, X, Y, and Z start? So it's, as you might imagine, you get further back in the Earth's history, details get a lot more fuzzy.
We're going to try a fuzzy question or two. Okay.
So there's no reason why we expect an island arcs to eventually form off the east coast.
If I were to predict, I would say that the East Coast will eventually turn into like the West Coast of South America. So we would eventually start to get that Atlantic Ocean crust subducting underneath North America. So you know how the Andes are all down the western side of South America? That's probably a more likely scenario. There are some island arcs down in the Caribbean region down there. So a lot of the Lesser Antilles down there or island arc system. But I would expect that when things get interesting here, when that subduction does start, that it will start underneath North America. So the eastern margin of North America will look a lot like the western margin of South America now. I would say in 25 million years it'll be happening. There's no way you can check that. But that would be my prediction. Yes.
I know it's not your field, but what impact does the glacier have on the formation of the peninsulas and islands of Maine? They all kind of go the way the glacier drags back.
Yeah, that's a great question. So the question is with regards to the orientation of a lot of the peninsulas and islands in Maine, they have that north-south and northeast orientation. So they are not quite parallel to the glacial ice flow directions, but close. So there's two things that are kind of controlling a lot of the landscape, the morphology of the landscape. One is the orientation of the bedrock, which is kind of in that northeast-southwest direction because of that compression. I should say that that's in the metamorphic bedrock. A lot of the granites are these big blobs in there that don't necessarily have any orientation to them. Now the glacial ice kind of, if I go back to the diagram here, you see the glacial ice direction was coming down in a slightly northwest to southeast direction, so not exactly parallel to a lot of the peninsulas and things. So they certainly exerted a lot of control on morphologies, but it tends to be some of the smaller scale features that we see. So the glacial ice flow directions weren't exactly parallel to the bedrock features. So a lot of times you'll see ice flow striations that kind of cut across the layering in the bedrock. So they both are exerting control on morphology. And it just depends on the nature of the bedrock. And some bedrock is uniformly pretty resistant, like Mount Katahdin or down MDI, big granite that doesn't have any layering associated with it. But a lot of the peninsulas in Maine, they're metamorphic rocks that are very strongly layered. So that's why you get that orientation. Yep.
How deep do you have to dig in order to do your mapping?
Good question. I don't dig. I'll sometimes peel moss outcrops, but I basically go around looking for places where the rocks are poking out of the ground and look at them. So that's how I'm different from, say, somebody who's studying glacial geology. They might dig down into the sediments and say, okay, is there clay underneath here or sand? I'm pretty good with a rock hammer, but I can't get very deep, and it's expensive to drill a hole. So there are some people who do drill holes down
to try to get drill core out and get some three-dimensional information. But I just, if I go back to my geologic map, which is probably quite a ways back, there's a lot of extrapolation that goes on in forming a geologic map. Where in the world? Oh, I have a lot of slides. Here. If you see all those little blacks, the little dots, and then there are all other little symbols on there, those are places that I visited. Those are places where I found some rocks, I described the rocks, I measured some orientation of the rocks. Notice there's a lot of areas where I don't have any information. So there's a lot of extrapolating. I'd love to be able to get through all, I'd love to wash away all this glacial crap off the top of it so I could see. But, maybe you have, 1%, 3%, 5% exposure to bedrock. So there's a lot of extrapolation to form a map like this. So you may notice some of the lines are dotted, some are dashed. There's a lot of uncertainty there. So another geologist could come in here and make a map. In general, it would probably look like my map, but there would probably be some differences in interpretation. So it's a good point.
Do you expect the same processes to be on the other side of the Atlantic, in Scotland and the Hebrides and over there?
Yeah.
You've got a lot of fingered islands as well.
Yeah, it's the exact same geology. So I don't want to flip through slides again, but when things were rolling together, those were part of the same mountain rock. So sometimes called the Appalachian Carolines. So the rocks in Scotland, the rocks in Norway are almost dead ringers for what we have here. And so when they pulled it apart, when the Atlantic Ocean opened up, some of it went on that side, some of it went on this side.
Will the Casco Bay bedrock separate again from the North American?
Ooh, that's a good question. I guess if you had now we've had to wind the clock way ahead. If you did initially have subduction, then Europe and Africa come back, the Atlantic Ocean swashes over and gets closed again, and then eventually it will probably lift apart and open up. The question is, which side would it go on? That would be hundreds of millions of years in the future. Yeah, that'd be a tough one. Yeah, I have a little bit more confidence in the subduction thing, but not that one. Was there a question?
There was. So the question is, can you please comment on the isostatic rebound from the retreat of the ice and sea level?
Ooh, sounds like we got a ringer there. So, yeah, again, the weight of the ice depresses the Earth's crust. So, and then as the ice retreats, it takes several thousand years for the crust to come back up. So people who study the retreat of glaciers will study the rate at which sea level would back off, basically. And that could tell you something about the sort of isostatic adjustment there. So not my area of expertise. There's certainly people who study the details of how quickly ice, or how quickly the land surface rebounds back, and there's differences along the coast of Maine. So some places it rebounded more quickly than others, and so there's sort of differential isostatic adjustments that are found there. But you'd have to get a glacial geologist to provide more detail on that one. Yeah.
Outside your range of expertise perhaps, but talking about climate change, sea level, how long before the coast of Maine and down to Miami will be covered with ocean water? The Pentagon is much more concerned than most of our political leaders about this.
Right.
It isn't discussed very much. Oh, is it a 50,000-year period, or is it a lot less?
No, it would be a lot less than that, a lot less than that. So the question is with regards to sea level rise associated with climate change. So as I think the Greenland ice sheet has about 20 or 30 feet of sea level equivalent in the ice. If we melt Greenland, sea level goes up that much. Antarctica's got something like 200 feet of sea level equivalent, so if you melt down Antarctica, all that water goes in the ocean basins and it goes up. So, as these glaciers wax and wane, sea level goes up and down. So as global warming, particularly in the northern hemisphere, is accelerating melting of Greenland ice sheet, then sea level is definitely going to go up. The question that climate modelers are trying to unravel is how rapidly is that going to happen. And one of the things they do is they go back and look at Greenland. Remember I showed that diagram of all the ups and downs? What happened, when it went up and down? How rapidly did that happen? So there are a lot of paleoclimate people who are trying to understand, how rapidly things change in terms of sea level rise.
Is it true that Antarctica is mostly ice and nothing at all and no rock?
Well, there's land underneath there. It's just that the glacial ice is so thick down there, it's just depressed at below sea level. So there's isostatic, issues there. If you melted that, it would eventually pop back up. So it's like, if you look at the coast of Maine 13,000 years ago, most of it would be underwater, but it's now rebound back up. So there are places in Antarctica where the bedrock is poking out of the ground. But a lot of other places it's underneath all the ice. If that ice melted, it would rebound back up.
Any special reason why Portland's sea level is rising higher than after?
Question is there any reason why Portland's sea level is rising faster? I'm going to comment on that one. I don't have any expertise in that area.
So it's getting warmer.
Yeah, so global sea level is rising, it's measured in millimeters per year, so it's not going to be rapid. The other thing that can happen is the land surface could be subsiding. So there's always that, is sea level rising as the land surface subsiding? The most dramatic land surface subsidence usually occurs in places that are tectonically active. But there could be other reasons why the land surface might be, differentially subsiding.
It's just warming.
Yeah. Yeah.
Does the Sebago Pluton have an effect on the landforms the most?
Yeah, let's see. The question is with regards to the Sebago Pluton. I was trying to see if I could find a map that might have it on there. There's one that shows the edge of the Sebago. So that big pink mass over there to the left on that map, that's a large granite body called the Sebago batholith. As it turns out, from what we understand about Sebago, it's more of a sheet. It's not this big blob under there, it's more of a sheet that's under there. So it doesn't necessarily occupy as much volume in the Earth's crust as you might think. The other thing about Sebago is that it's a little bit younger than a lot of the other granites around there. There's quite a range in age of the granite, so you can see that some of the granites are shown as blue and some as pink. That reflects the different ages of them. So there's granites in Maine range in age. Well, like Cape Nettic, for example, there's intrusive rocks there that are 120 million years old. And then there's some rocks up in northern Maine that are 460 million years old. So there's a huge range of granite ages in the state that reflect different tectonic processes. Yeah.
I have a question on the water. What would cause all the continents to come together? And wouldn't that throw the spin of the earth off? And do we have any idea when that continent was in relation to the axis?
Yeah. So the question is, what is sort of the impact of the larger scale of global implications of having a supercontinent? If you have a supercontinent, you probably have a super ocean too. So there are a lot of issues there. one of the interesting things, and it's not a coincidence, is that the largest mass extinction event in Earth's history coincided with the amalgamation of all those common land masses in Pangea about 245 million years ago. So, it certainly disrupted ocean circulation, which distributes heat, so there was radical climate change. Think about the interior of that huge continent, probably pretty dry. So, now, whether it had an impact on, differential sort of global scale distribution of mass, it's hard for me to say. My guess is that the Earth's crust is so thin relative to the overall mass of the Earth that it probably wouldn't have a significant effect on things like